So we want to test if this function is differentiable at x equals 0. One way to do it would be to test if the left-hand derivative and right-hand derivative are equal to each other. Another way to do it would be to actually graph the function and then try to see if those derivatives exist. But let's take a look at how the graph looks like. So this is a nice piecewise function we're looking at. So f is 2x minus 1 when x is greater than or equal to 0. So plug in 0, you would get 2 times 0 minus 1, that's negative 1. So when x is 0, you are at negative 1 right here. And it's a line going upward like that. So that is f of x equals 2x minus 1, roughly sketched. Now, when x is less than 0, then we're looking at this function. X squared plus 2x plus 7, again plug in 0, you get 7. So when x is 0, we get 7. Let's suppose 7 is up here, and it's going to be an open circle because x is strictly less than 0. And it's a parabola, so the parabola will be facing up, something like that. Now we're testing if it's differentiable at the origin. Well, it's not even continuous at the origin. There is a big jump, right? So because of that, it's not continuous. There is no way we can talk about differentiability. So this function, f, is not differentiable at x equals 0 since it is not continuous. So it doesn't make sense for us to talk about if the function is differentiable at 0 because there's no derivative at 0. Here is another one we can look at. Is this function differentiable at x equals 0? So again, you can test the right hand and left hand derivative, or you can simply graph it. Now sometime by graphing it, it might not be clear, but let's take a look at the graph just in case you are wondering how this looks like. So x to the 2/3, well, that's a nice continuous function, but we're only looking at that piece when x is greater than 0. So it looks, roughly drawing, it looks something like this. And then x to the 1/3, when x is less than 0, well, x to the 1/3 will also look something like that, but it's going to look maybe something like this. So that's the graph of g of x. So this is the entire graph of g of x. So we want to know, is it differentiable here? So that's the question. Does the derivative exist at x equals 0? So it's probably not clear to you by looking at the graph. It's continuous, but that's not enough to find if it's differentiable or not. But the function must be continuous. So that's one checkpoint. So we want to show that the limit as h approaches 0 from the left of this function is equal to the limit as h approaches 0 from the right. So we're testing the left and right hand derivatives. So let's go ahead and check this out. So for the left hand derivative, so the limit as h approaches 0 from the left, so from the left hand we're going to use this function, x to the 1/3. So we're looking at g of 0 plus h minus g of 0 all over h. Sorry, g of 0, I meant to write that. And then plugging 0 plus h into the function. So we have the limit as h approaches 0 from the left. So 0 plus h to the power 1/3 minus 0 all over h. And this would give us the limit as h approaches 0 from the left, h to the 1/3 power over h. And then we simplify, so we subtract their exponents by using laws of exponent. This is the limit as h approaches 0 from the left. So you're doing 1/3 minus 1, so that's going to be negative 2/3, or simply 1 over h to the power 2/3. So once we have done that, we see that we're plugging in a number 0 from the left. So very small number from the left approaching 0. So this will give us plus infinity. So that will be this limit. So we see that this limit is not finite. It is positive infinity. Now let's go ahead and test out this one. So we are now looking at the limit as h approaches 0 from the right of this function g of x. So let's use the limit definition. So we're going to apply the limit definition here. So we have the limit as h approaches 0 from the right, g of 0 plus h minus g of 0 all over h. And then this would be the limit as h approaches 0 from the right. So we're using from the right, so that's going to be this function right here. So we're approaching from the right, we'll be using x to the 2/3 as our function g of x. So we have 0 plus h to the 2/3 minus 0 to the 2/3 all over h. And then here I can simplify this like we did before. This is the limit as h approaches 0 from the right, h to the 2/3 minus 0, or we can just simply ignore that part, all over h. And then here, of course, you simplify the exponents, so you do 2/3 minus 1, which would be negative 1/3. And then this is going to be the limit as h approaches 0 from the right, 1 over h to the power 1/3, since we had negative 1/3 on top. So now let's take the limit. So if you approach 0 from the right of this function, you will get plus infinity. So you see that both of these limits happen to be not finite. So we can conclude that although they're both equal, right, they both happen to be same in plus infinity, but they're not finite. So because the limits are not finite, we can conclude that there is no derivative at x equals 0. So this means g prime at 0 does not exist, because the right-hand derivative and left-hand derivative, they are equal, but then they're not finite. Now, if they were unequal, then of course the derivative doesn't exist. In that case, your tangent line will have an undefined slope. Here, you can imagine that there is a tangent line at x equals 0, but the tangent line is vertical. So this is a vertical tangent line. All right, so this is it. I hope this makes sense.